Hello. This talk will present the derivation of the rotation matrix for rotations around the origin in R3. It's taken from section 2.3.6 of the current draft of the book. So recall that the rotations that we've been using are R theta u, and these rotate angle theta around the axis u through the origin, and the direction is given by the right-hand rule. So the direction is by the right-hand rule. Okay, so as before I derive the matrix, which is a rather complex looking matrix, let's just as a warm-up do an example. So for example, let's consider R pi over 4 I. So what does this do? We're rotating around the axis I through 45 degrees, pi over 4 radians. So if we draw our coordinate system here, here's the x-axis, the y-axis is up, and the z-axis is coming out of the board towards you, towards the viewer. And we're rotating around the x-axis. The unit vector I, of course, lies along the x-axis. Right-hand rule tells us that we're going to be rotating this way, following my fingers in the right hand as I point my thumb out the direction of the positive x-axis. And so what this is going to do is it's going to bring what's this going to do to the x, y, and z axes? It's going to leave the x-axis fixed because we're rotating around that axis. It's going to lean the y-axis 45 degrees forward. It's going to push the z-axis 45 degrees down. So we can just write immediately the 3x3 matrix for this by just looking at the actions, the rotations on the I, J, and K vectors. So we have that R pi over 4 I of I is just I. That's a fixed vector. R pi over 4 I of j. So here the j vector gets leaned forward 45 degrees. So it's going to be the square root of 2 over 2 times j plus the square root of 2 over 2 times k. And then r pi over 4i applied to the k vector. So now the k vector is being pushed down 45 degrees. So that'll be minus square root of 2 over 2 j plus square root of 2 over 2 k. And we can fill in the 3x3 matrix as just using the columns. So the first column is the image of I, that's 1, 0, 0. The second column is the image of j, so it's 0, square root of 2 over 2, square root of 2 over 2. And the third column is the image of k, so it's 0, minus square root of 2 over 2, square root of 2 over 2. So here we've got a very simple way to visualize what this matrix means. We look at what the rotation does to the I, J, and K vectors. We fill in the columns with those values. And there's our 3x3 matrix. There's no translation parts, so it's a linear map, so we can get away with a 3x3 matrix instead of a 4x4 matrix. So we would like to generalize this whole process to an arbitrary vector u. We're going to take an arbitrary unit vector, a vector of length 1, and we get a formula for a 3x3 matrix that represents the rotation. So for this, we're going to make an assumption here is that we let u be a unit vector now. So the length of u is 1. The magnitude of u is 1. That'll just simplify things. In general, our conventions are that it doesn't matter what the magnitude of u is when we define r theta u. If we scale u, it doesn't change the rotation. The rotation amount is given just by the theta value. So here's the formula for the rotation matrix. I'll write it loosely as r theta u. It's going to be given by the following 3x3 matrix. So it's a rather big matrix, so I'm going to shut up for a moment and just write on the board without saying anything, and you'll be able to see me go by in fast motion. So I think this is all written up. Let me just clarify some things here. This is where the vector u has components u1, u2, u3, and where c equals cosine of theta, and s equals sine of theta. So it's a pretty big matrix, right? Very complex. And by the way, I should just say right now, do not memorize this. You should be able to figure out the matrix for simple rotations by hand, just like we did with our pi over 4I a moment ago. For the big matrix, it's a nice formula, but it wouldn't be something you would normally just do by memory. Actually, the important part of this is really how do you derive the matrix. That's really the more important part, rather than the actual formula itself. So I'm going to prove this in stages. Let me just break this down a little bit. You'll notice a bunch of 1 minus c's floating around. You'll notice there's some c's on the diagonal. You'll see here that there's like a u1, u2. This is like a u1 times u1, u1 times u3. So I've got a bunch of entries of like a ui times uj, uj factors in column I and row j, or vice versa. These are going to correspond. These parts come from a dot product. Okay, that we'll talk about in a minute. And you also see these plus or minus SUI. It's plus SU3, minus SU3, minus SU2, plus SU2, and so forth. And then there's these plus or minus SUI factors, and these parts come from a cross product. And we'll see that coming up in the next derivation. So we're going to see matrices that express both dot product and cross product. And the C's will come from an identity matrix, actually. So we'll see where all those come from in the next few lemmas. I'm going to prove a lemma 1a and lemma 1b for projections and dot products, and lemma 2 for cross products. And then we'll come back and prove the correctness of this matrix for R theta u. Okay, so our first lemma 1a, I'll call it. And by the way, this numbering is not used in the book. I'm doing the proof a little bit differently on the board than in the book. So we let u be a unit vector, and we'll let v be any vector. We're going to think of u as fixed, so we're going to be holding u fixed, but letting v vary. But we want to start off with the projection of v onto u is equal to, I'll call it, in fact, v1, that's a vector, v1. v1 is equal to u dot v times u. So this is dot product here. Okay, so u dot v is a scalar, so it's that times u. So this probably is a familiar lemma to you, but let me remind you how this works. The proof, I'll just do a sort of picture here. I've got the unit vector u, length 1 vector u. Think of the origin as here. I've got some other vector v. Its projection onto u, is what we mean by that, is the vector that the component of v in the direction of u. So the projection is a vector. It's in the direction of u, or could be in the negative direction of u if v is over here. And it's obtained by dropping v perpendicularly down to the line containing u. So in particular, the length of the v1 is equal to the length of v times cosine of phi, where phi is this angle between u and v1. Okay? And on the other hand, we know that u dot v is equal to the length of u times the length of v times cosine of phi from our earlier knowledge of dot products. And we have that the length of u is 1. Minor correction here. I should have really put absolute value signs here. Because cosine of phi could be negative if it's pointing over this way. But in particular, what we have then, from this, we get that v1, the projection, is equal to length of v times cosine of phi times u. Because this is the signed length of the vector v1, and the direction of v1 is in the direction of u. With positive sign, it's this way. With negative sign, it's this way. Okay. And so now from this, the lemma follows immediately. Okay, because we have that u dot v times u is equal to the length of v times cosine of phi times u, since the length of u equals 1. Okay, so that proves lemma 1a. So now let's talk about lemma 1b. This is the matrix form of lemma 1a. It's still talking about the projection, but now we're going to get a matrix that gives us the projection. So again, let u be a unit vector. Okay, and we're going to, again, u is fixed, and we let v be any vector, as before. We're thinking v is varying. Then the projection of v onto u is equal to v1 equals proj sub u. This proj is short for projection. Sub u depends on u times v. Where, I need to tell you what proj sub u is. Proj sub u is the following 3 by 3 matrix. It's got u1 squared, u1, u2, u1, u3, u1, u2, u2 squared, u2, u3, u1, u3, u2, u3, u3 squared. So we've got a 3 by 3 matrix that gives us the projection. So we're going to prove this by using some matrix things. Just even to rewrite this matrix, we can rewrite this matrix as the column vector u1, u2, u3 times u1, u2, u3. So here, I should have mentioned that the vector u is u1, u2, u3, which of course we think of as a column vector, as always. We put angle brackets there to indicate that it's really a column vector. Okay, and again, to see why this equality holds, we take the u1 times u1 gives us this first entry, u2 times u1 gives us the second entry, u3 times u1 gives us the third entry on the top row, and so forth. And so this all just, you can check all the entries are correct. And we can write this again as u times u transpose. So the t here means transpose. the operation in here is matrix product. And we're thinking of U as a 3 by 1 matrix and U transpose as a 1 by 3 matrix. So this is U right here, and this is U transpose right here. And we're multiplying them as matrices to get proj sub U. So this puts us pretty much set to prove lemma 3, so lemma 1b. But first, let's also notice the following claim, is that if x equals x1, x2, x3, and y equals y1, y2, y3 are vectors in R3, then x dot y, and this is dot product, is equal to x transpose times y. So again, this is dot product here. This is matrix product here. We're thinking of x as a 3 by 1 matrix, y as a 3 by 1 matrix, x transpose as a 1 by 3 matrix, it's a row vector. And when we take the dot product, the proof of the claim is you just notice that x transpose is x1, x2, x3, and we're taking that matrix product times y1, y2, y3. See, this is x transpose y, and that's the same as x dot y if you identify the 1 by 1 matrix with a scalar, because to evaluate a 1 by 3 matrix times a 3 by 1 matrix, you just take the inner product of the row with the column, and we get the dot product. So now we're ready to prove lemma 1b. So we know that v1 is u dot v times u by lemma 1a. So this is a scalar times a vector, so that's the same thing as, we can reverse the order, vector times a scalar is the same thing, so that's the same as u times u dot v. Now by the claim, u dot v, let's change these to matrix products, u dot v is the same as u transpose v. So I've just changed the dot product to a matrix product with the transposed vector there. And then we can do associativity, so that's the same as u transpose times v. This is by associativity. And by what we marked up here, that's just proj u. And that proves lemma 1b. I did a somewhat abstract version of the proof here. You could have also proved lemma 1b by just breaking everything into coordinates and working directly with that. But this is a little bit more abstract, and it brings out nicely what's going on with the vectors. So now we can state lemma 2. So let u be any vector. We're going to be thinking of it as fixed. It no longer needs to be a unit vector, although we will be using this with a unit vector. Let z also be a vector. Then u cross z is equal to m u cross, which I'll define in just a second, times z, where m u cross is equal to the following 3 by 3 matrix: 0, U3, minus U2, minus U3, 0, U1, U2, minus U1, 0, giving the elements in column order. So what's happening here is we're mu cross is a 3 by 3 matrix. If we multiply it with a column vector z, we get another column vector. Of course, the cross product of three vectors is another 3 vector. So that makes sense. The other comment is that if you hold u fixed and just think of this as a function, u cross z is a function of z, it's clearly linear, so it has to have a matrix representing it. So what matrix should it be? Well, it's this one. The same things happened in Lemma 1b. The projection operation on, we called it v back then, is linear in v if you hold u fixed. Therefore, there's a matrix for it, and that was the projection sub u matrix. Okay, so the proof here is a little more straightforward computation. So let z be the vector z1, z2, z3. Then if we take 0, u3, minus u2, minus u3, 0, u1, u2, minus u1, 0, and we multiply it by z1, z2, z3, well, we just work out what's going on here. The first entry is the column vector inner product of the top row, so that's minus u3, z2, plus u2, z3. The next one is the column vector inner product of the second row, so it's u3, z1, minus u1, z3. Let me fix the typo there, that was a z3. And then finally we take the column vector with the bottom row, and we get minus u2, z1, plus u1, z2. And that's just equal to u cross z. These are just the familiar components of the cross product. So that proves lemma 2. So again, the point of lemmas 1b and 2 is that familiar matrix operations can be re-expressed as, try that again. The point of lemma 1b and 2 is that familiar operations such as dot product and cross product, since they're linear, if you hold one argument fixed, they can be re-expressed as matrices. We've given examples for matrices for cross product and for projection. So now we're ready to prove the derivation of the rotation matrix. So let's derive the derivation of the 3 by 3 matrix for R beta u. So let me recall that u is a unit vector, so it has length 1. And what we're going to do, let me draw a picture of this here. I've got some vector u sitting here, length 1, and I've got some other vector v sitting somewhere in 3 space, what I want to rotate around u. So what we're going to do is we're going to start by breaking v up into its parts that are parallel to u and orthogonal to u. So we're going to take the projection of v onto u, and we'll call that v1, and then we'll take the orthogonal component, and we'll call that v2. So in particular, v1 equals proj sub u of v, and v2 is v minus v1, and so that's equal to the identity matrix minus proj sub u of v. So we've got a 3 by 3 matrix for proj sub u. We've also got a 3 by 3 matrix for I minus proj sub u, because I is a 3 by 3 matrix. And then we're going to notice that r theta u of v, by linearity, is equal to r theta u of v1 plus r theta u of v2, just because rotation is a linear operation. But v1 is in the direction of u, or in the negative direction of u, so that's just equal to v1 plus r theta u of v2. So we've got a matrix that gives us v1, a matrix that gives us v2. Now we need to figure out what the rotation matrix, rotation operation does to v2. So for this, we're going to change our point of view. So in this picture here, v is sort of getting rotated around this way, or v2 is getting rotated around this way through some angle theta, right? But it's a little hard to picture the way we've drawn it on the board. So let's instead do a top view. So for top view, what we do is we've got v is in the center, u is in the center, pointing straight out of the board. So I'm looking straight down towards the head of u, and u is pointing up towards us. And then v2 is here at right angles to u. And then I'm going to form a new vector, v3, which is orthogonal to both u and v2. And the formula for v3 is that v3 is u cross v2. Why? Because we're thinking of u is pointing outward. We take the cross product right-hand rule, we push u towards v2, and we get a vector that's at right angles pointing upward. And we have that the length of v3 is equal to the length of v2, since u is a unit vector. Right. So when we do the rotation here, if we rotate through angle theta, we're just thinking of rotating the v2 portion. We've set v1 aside, so that no longer comes into it. So everything is orthogonal to u. And we want to know, if we drop the perpendiculars to do these two things here, this length is going to be cosine of theta times the length of v2. So it's going to be length c times, well, it's actually going to be literally c times v2 is that vector. And this vector here is going to be s times v3. The sine of the angle times v3 will give us this vector here. And so, in other words, what this tells us is that r theta u of v2 is equal to c times v2 plus s times v3, and v2, that's the same as plus s times u cross v2. And so now we're almost done with the derivation. So again, what do we do? We broke v into two components. The parallel component to u, and that doesn't change. It just stays as v1. The perpendicular component, that's v2. We switch to the top view. We get the other perpendicular component that's orthogonal to v2, and we use that with sines and cosines to express the rotated vector here. So this vector here is r theta u of v2. And that's equal to, as I wrote here, cv2 plus sv3. One final simplification we can make is that this is equal to c times v2 plus s of u cross v. So before I had s of u cross v2, and now it's just s times u cross v. And the reason for that is that since v minus v2 is v1 and is parallel in the same direction to u, so u cross v1 is 0, so therefore u cross v2 is the same as u cross v. So that's basically the idea of the derivation of the matrix. All that's left is to put all this back together. And I'll do that on the next board. So putting this all back together, I've got r theta u of v is equal to, well, v1 plus c v2 plus s v3, and that's equal to proj sub u of v plus c times I minus proj sub u of v plus, and now I need to erase more, plus s times m u cross of v. And I'm using v here instead of v2 as I remarked at the end of the previous board. So we can rewrite that as 1 minus c times proj sub u of v plus c times the identity times v plus s times m u cross times v. And breaking this up into one big matrix, this is in square brackets 1 minus c proj sub u plus c times the identity matrix plus s times m u cross, that whole matrix times v. And so this part here in square brackets is the 3 by 3 matrix representing r theta u. And this is, when you expand it out, it's exactly the matrix I had on the other board. So exactly the large matrix shown before. So again, to repeat myself, the point here is not to memorize the big matrix. Sometimes people do memorize it for tests in this class. I don't really recommend it. I mean, it works fine, but I don't really recommend it. Instead, usually, if it's a simple rotation like around an axis, you can just figure it out by looking at the columns. It's a far more robust and repeatable way to do things. The important thing here really is that a lot of these linear algebra operations, like dot product or projection or cross product or linear, so they've got matrix representations. And this is part of just sort of the tip of the iceberg of why matrices get used so much in OpenGL, because they're so useful for so many things. So that's it for this presentation. Thank you very much.